Well, good afternoon, everyone, and welcome to the EOL seminar series. I'm pleased to welcome Professor Raffalski, who comes to us from the Swedish Institute of Space Physics. Professor Raffalski obtained his PhD in physics from the University of Bremen. His PhD thesis, published in the Reports on Polar Research, was titled Observation of Stratospheric Trace Gases over Ny-Ålesund, Spitsberg, using a ground-based microwave radiometer. Professor Raffalski joined the Swedish Institute of Space Physics, where he is responsible for the development, maintenance, and operation of the Swedish millimeter wave radiometer called KIMRA, K-I-M-R-A. He is also involved in the planning and construction of the German microwave radiometer for the German Polar Research Station in Svalbard. Professor Raffalski gives lectures on microwave radiometry, space technology, and atmospheric chemistry of the ozone layer. His scientific interests span observations of the Earth from both the ground and space, particularly measurements of atmospheric trace gases, the ozone layer, and global climate. Most recently, Uwe provided collaborative support for EOL and the CESAR science team while they conducted field observations from Kiruna, Sweden, with the NSF NCAR C-130. Nearly the entire CESAR team also made good use of the Institute's publicly available all-sky camera for facilitating optimal viewing of the aurora borealis. For those online, welcome. You can type your questions on the Slido window, and we will have a Q&A session after the speaker's seminar. So please join me in welcoming Professor Raffalski as we learn more about research in the Northernmost Scandinavia, a brief overview of activities at the Swedish Institute of Space Physics.
Thank you, Becky. Thank you. And what do you say? Good evening, good morning. I'm a bit confused because the time lag hasn't really left me. It's nice to be here and to pay back. I mean, when Corey and the staff was in Kiruna, you and others came to IRF and even presented the work that you're doing. You had a wonderful open day for the Kiruna community at the hangar. So I thought when I come to a conference here in Boulder, I should just drop in and present our institute here so that you get a view of an institute from a different place in the world. How should I start? Probably I just open the presentation here and start with an overview, what I'm going to present. I will give you a little bit of a flavor of Kiruna. Not everybody of you has been there, so I start with some pictures, and then I will go to the observatory activities that we have at IRF, our institute, go to the space research, which is a little bit a newer research part, and then in the end, of course, atmospheric research is the thing that you probably are most interested in. Just a disclaimer here, the ozone data and analysis that I show in the end is also made by my colleagues Matthias Mills and Richard Johansson. Okay, what idea do you have about Kiruna? Have you ever been there? Do you know anything about it? Then, well, probably you have heard Kiruna is the hinterland of Sweden, where the mooses are running around. The winters are not that good. The end of August, it was snow, and that is my little daughter, Sarah. And that is our way to work. It is really a tough environment there. And those of you who have been there, yes, it was tough. But that is not all that you can say about Kiruna. And that's the flavor of Kiruna I wanted to present a little bit, at least. We have one of the largest, if not the largest, underground iron mine. The trains going from Kiruna to Narvik, 13 a day, are drawn by the strongest locomotive in the world. And these trains, they have 64 wagons, 50 tons of iron every day, and that's quite a lot. And the mine, you can see there is a cut through the mountain, and it goes down. The main layer is at 1,300 meters below ground. Okay, then of course people probably have heard about the ice hotel. It's another thing that is well known in Kiruna, built every year. And since a couple of years back, we also have a ice hotel year-round, ice hotel 365. So if you come in the summer, you can even sleep in an ice hotel. That is, well, it is also known for Kiruna. But that, of course, is very nice to see and watch in Kiruna. I don't know how much opportunity you had to see these kind of aurora. We are heading for a solar maximum next year. So if you plan for a new campaign, think about that. So the aurora, of course, is one of the reasons why our institute has been founded in Kiruna, because it's a very nice place. It's a good location to do aurora observations, and not only taking nice pictures, but also do research. And talking about research now, another place which is quite well known in the research community, that is ESRange, where huge campaigns are launching balloons or even launching rockets with scientific equipment. And when I started at the Institute of Space Physics in 1997, it was just about the big ESO campaign. No, the ESO campaign has passed. There was this SAGE campaign. It was in 2000, which started in Kiruna, and there was a big balloon. It was the DC-10, and it was the ER-2 at the hangar in Kiruna. So that it's quite a big place to do science, Kiruna. That is what I wanted to show with these pictures. And that, of course, is coming closer to atmospheric physics now. It's a mother of pearl clouds, PSCs, polar stratospheric clouds, that we can see almost every year, depending on the meteorology, depending on the temperature in the stratosphere. And in the picture to the right, you can even see the mountain of the mine. But this is where Kiruna lies. And if you compare with the other places around the polar circle, it's Siberia, it's northern Alaska, and it's northern Canada. We still have quite a good infrastructure, and I think that is also one of the reasons that these big campaigns can start in Kiruna, and because we are also closer to the polar vortex than if you fly from Canada or Alaska. That is also the place where it all happens. So let's go to the details here. That is the campaign that I talked about, the ER-2, the DC-10 at ESRange, the SOLVE, not SAGE, it was SOLVE campaign 2000. And that is the recent campaign that we had in Kiruna. The upper one you probably can recognize, but the lower one is the German aircraft, Polar 6, I think it is. We don't have that much money in Germany, so the airplane is a little bit less fancy than the ones that you have. It's actually a DC-3, which was built during the World War II. It's still flying. But the pilot says there is hardly any original part in the airplane anymore. Okay, Kiruna. Kiruna lies over there on the top of Sweden. And this is Scandinavia. For those who are not so familiar with other places than the US. But Kiruna is only the headquarters of our institute. We have 3 other places in Umeå, in Uppsala, and in Lund, where people from the IRF, from the Institute, are sitting and working with different tasks. And I will come to that in a minute. We have around 110 employees at IRF in total, 50% scientists, 50% engineers and administrative staff, which is quite a good balance. Usually you have much more engineers and administration than you have scientists on board. And we think that we are quite lucky with 50% scientists. Our budget, 111 million Swedish krona, yeah, roughly 10 million US dollar. It's not that big. I don't know about your budget, but this is quite a small institute. It's the last institute which is still independent in Sweden. All the other institutes have disappeared in universities. We have engineering courses, or we help with engineering courses with the University of Luleå and Umeå, which is located at the campus as well. And also we have a lot of PhD students. No, this one. At the Institute, we have 3 research programs and one observatory program, you could say, or observatory activities. The 3 research programs I will present a little bit briefly. Even the names are not so much different. So when I started at the Institute, I had problems to keep them apart and understand what the differences are. It's solar system physics and technology and space plasma physics. Those are 2 programs which build experiments flying in space, mounted on satellites. And then we have the solar terrestrial and atmospheric research, which I belong to. And we have ground-based, mostly ground-based instruments, but looking up into the sky as well. Okay, let's start with the observatory, because that is also the historical start of the Institute, founded in 1957. At that time, of course, not with 40 instruments. The reason was that we wanted to have ionosondes and detection of the magnetosphere, magnetometer, and stuff like that, mounted somewhere in the wilderness. And Kiruna was a good place to do that. And it is also not so populated, so that you can keep the instruments away from the public, so that they are not disturbed. These are magnetometers in one of the huts that you can see there. And these magnetometers nowadays, they are very, very sensitive. You cannot approach these huts with your watch or with a key or something like that. You have to make sure that your ring is off if it's in some kind magnetic. So the huts were built long time ago, even and they were all built of wood. So all steel nails, they have been checked whether they are magnetic or not. So the magnetic ones have not been used. So this is magnetometers. Later we had also cameras installed in different places. You can see the places in the picture to the left. Small huts, as shown in the picture, with cameras on top looking up into the northern light. And if you have different places, you can do tomography of the northern light. And that was the plan from the beginning, to put up a lot of cameras, They are digitalized nowadays. In the old times, we had even film cameras there, and those who made a visit at IRF, they have seen these film cameras. And at the right, you can see the magnetometer, which shows a lot of activity at the left side of the graph, and there you can also see the strong aurora, which has been photographed by the cameras. And then the magnetometer line flattens out, but also the weather turned bad, and we don't see any northern light anymore. Okay, that is cargo, and then also in the good old days we had some of these antenna activities, ionosondes and radiometers. I'm not an expert at all with those. I just know that they in some way they detect the properties of the atmosphere with respect to incoming radiation or even the change of the solar wind and stuff like that. And since 1972, we even have infrasound observations continuously, and well, that is part of the cargo instrumentation. And this is the latest part. This is the part where I come into play here. It's a DOAS instrument, the millimeter wave radiometer, the FTIR, and another millimeter wave radiometer to the right. And those instruments, they measure trace gases in the stratosphere. But before I come to my expertise, I should just have a short detour in space. This is the satellite Viking, first Swedish research satellite, built at Esrange with the help of our institute. This is Astrid. You probably know Astrid Lindgren, the writer who wrote about Pippi Longstocking, and some of her figures in the different stories are Mio, Emil, and Ronja, and the instruments on this satellite, they were called after these persons in Astrid Lindgren's stories. We got even an approval letter from Astrid Lindgren that we can use these names for the satellite. This is the latest development at our institute, the biggest project we ever had at our institute. It is 2 contributions to the JUICE mission, the mission to Jupiter. So it's planned to fly by some icy moons around Jupiter and to see whether there is water and what kind of conditions there are and whether there has been life in space. Okay. I leave it like that. It's 10 instruments, and our institute is pretty proud about that we put 2 instruments, 2 out of these 10, on this mission. I mean, this was an international call, and everybody wanted to fly to Jupiter, and we could get 2 instruments, this small institute, 2 instruments on board. It's quite good. A large solar wings to supply the power, and we are planning 35 Jovian moon flybys. It is still on its way. The launch was, I don't know, 2 years ago or something like that. And it will reach Jupiter in 6-7 years, and then they will start measuring. And most of the people who were PI or important scientists for this mission, they have retired at that time. But that is probably, that's the problem with these kind of big projects in general. That's how it should look like in the end. Okay, but we are also flying to smaller objects, like, yeah, I have to read it. Comet 67P, Churyumov-Gerasimenko. It's a tough word. It is a small comet. You probably have heard of it, and it's, I think it is like 2 kilometers in one direction or so. It looks like a duck, this yellow duck that you have in your bathtub. It's looking like that. And Rosetta was flying in front of it all the time when the comet was flying closer to the sun, around the sun, and then back away from the sun. And I will give only 3 slides of the science from those space experiments, and one of them shows this flyby like this. So IRF is contributing to quite a lot of instrumentation in space. We are a small institute, but still we have, I think it was 6 or 7, the last count was 6 or 7 planets that we have instruments on the way to or flying around. It's only the outer ones that we don't reach so far. That's how the instruments look like. I don't go into details, but you can see some kind of development from 2000 to 2018. It's also fancy materials which are used, and they are all built in our institute. We have a very skilled workshop which can do amazing things. First picture of the science there, the instruments that we built, that I've shown, they are all mass spectrometers, so to say. They fly and they collect particles coming in with a certain energy from a certain sector, and they are detected, and from their energy, their direction, we can do these kind of pictures. We have Venus, an instrument flying around Venus, and from these flybys you can do measurements. Where do the particles fly? Where do they come from? Where do they go to? And in this case, it is the solar minimum and the solar maximum shown left and right hand for oxygen and hydrogen ions. And well, if there's solar minimum, the sun is not very active, then there is not much particles coming from Venus or flying to Venus. But when there is solar maximum, there you can see these blue boxes which show that there is much more particles flying towards or away from Venus. That is one thing that we measure. This is the moon. We have an instrument on a rover on the moon and also flying around the moon. And this is the outflow of what is it? Neutral hydrogen, right, from the moon. And the solar wind, which comes from the sun, does some sputtering, so to say, on the moon, and the moon reflects due to the regolith on the ground. This is the third picture. You can see in the middle of the, this is the comet experiment. We fly with the comet close to the sun, around the sun, and then away from the sun. And during the season where we fly towards the sun, we can see that okay, now I have to use this. We can see that to the left on the upper panel, you have quite some inflow, or you have ions from the solar wind that you can measure. And then in the lower panel, in the middle panel, you can see the activity from the comet itself, the outflow from the comet. Then we reach a region where there is almost no contribution from the solar wind. That is the middle in the upper panel. That is when the activity of the comet is so strong that there is hardly any particles from the solar wind reaching or passing the kind of magnetosphere that there is. And once the comet leaves the sun again, you can see on the right-hand side that on the upper panel that the solar wind comes in again, and we do measurements with the particles there. Okay, so that is all I wanted to show about the space science. Besides, we also have a nice facility to test things. So if you ever break something on your airplane, I heard some things went wrong, then IRF can help with the workshop, and we have done that. And this is Space Lab. This is a test facility for even future activities. And S-Range has now come into play with launching satellites into the orbit. So there might be a necessary test place where you can put things into a vacuum dewar and cool it down to low temperature and test your instruments before you launch it with the rocket. This is Space Lab. Okay, but now for the rest of the time, I don't know how much time I have, we will talk about the atmospheric research. This is the institute, as you can see it from a little bit far away with the drone. We have the optics lab, well, with the red circle. And it's quite a lot of instruments that we have there. Quite a different set of instruments. Some do measure year-round. Some need the sunlight, and they don't measure during that the dark period. But it's quite a lot of instruments there, and I will show some of them. This is the STAR research program, Solar, Terrestrial, and Atmospheric Research. So that research actually covers the entire altitude, entire region from the ground to the sun, from the solar wind measurements to the magnetosphere measurements and down to the ionosphere and to the stratosphere in the end. One part of the STAR research program is also, of course, these aurora observations and the polar stratospheric clouds that you can see in the middle. And the picture further down is a picture of noctilucent clouds that we hardly see in Kiruna, but sometimes we can do that. There is a certain time period where you can observe noctilucent clouds because you meet very cold conditions in the mesosphere at 85 kilometers, and you still need some kind of night. And that is something that we don't have in Kiruna very often. The time period is from middle of May to the middle of August, and that is almost a bright season in Kiruna. Okay. And this is now the pictures of the aurora observations. There's the camera over there in the lower right, and there is other measurements in one of the domes that you could see from the roof, where we measure OH. It's the OH imager, which can show waves in the atmosphere. Okay, then we have the noctilucent cloud camera network. We have LiDAR, which you can see in the middle of the picture. And sometimes we also use sounding rockets. And there was an experiment just last year where we sent up some barium canisters. I will come to that in a second. Oh, right, it is here. That is it is the latest rocket experiment that we had. It's a rocket that was launched at S-Range, and on top of the rocket there were 8 canisters of barium, which were released at certain points, and that was a very, very nice view in the sky because barium is. Appears like a bright spot in the sky, and then you can see how the wind drags the barium away, and that is what is used to understand the dynamics of the mesosphere up there, the winds and the wind shear and all this stuff. So I forgot to put in some pictures, but you can look that up at our homepage. And then we have this IceGuard Scientific Association. It's a radar facility at quite close to the institute. It's the antenna to the right, where it says KIruna VHF. And this is a system of antennas to observe the ionosphere and a little bit higher up as well. The antenna in Kiruna will be dismantled, so next time you come it will probably not be there anymore, because there is a new technique where you can change the direction of the radar beam. That is an antenna field of 10,000 Yagi antennas each field, and we will have 3 or 4 fields in northern Scandinavia and do even better research. And don't ask me what this research is about. It's the ionosphere, it's the situation, and it's probably also dynamics over there, up there. But if we go into the optics lab now and have a look at the instrumentation there, we have quite a number of guest instruments, which are from different institutes. The FTIR is from Karlsruhe Institute of Technology in Germany. The DOAS is from Max Planck Institute for Chemistry in Mainz in Germany. RASPAM, a millimeter wave radiometer for water vapor observations, comes from, I forgot that, I should have written it down. It's also from Germany. Max Planck Institute for Solar System Research. And the MIRA 2 is an instrument, a millimeter wave instrument from Karlsruhe Institute of Technology, which together with my instrument does the ozone observations that I'm going to present in a minute. Why do we do these observations in Kiruna, and why is it good to do it there? You can see the polar vortex. It changes quite a lot. This is just 2 weeks apart. You can see elongation. It splits up, and 4 days later it's together again. That is the polar vortex. And Kiruna is mostly inside or at the edge of the polar vortex, which means if you do ozone observations, you would expect ozone depletion only inside the polar vortex and not outside. And that's why it's very fortunate to have a measurement inside the polar vortex during the entire winter. Then you can really do analysis of ozone depletion and change of ozone over the years. And the polar vortex is quite a big thing, so it's 5,000 kilometers. Yeah, the arrow is 5,000 kilometers, so you can see it's quite a big meteorological system. And if you are, this is also from your colleagues at NASA, if you are interested in ozone and the ozone chemistry, then you do measurements, for instance, with this aircraft here, and you measure CLO and ozone, and you come from the outside of the vortex, you have high ozone, low CLO, chlorine monoxide, and you pass the polar vortex and the CLO jumps up, the ozone falls down. So that is actually the interesting part of the polar vortex, that you can do this kind of measurements inside the vortex, and sometimes you are even outside and can do this kind of comparison between the two trace gases. Unfortunately, my instrument, which was designed for CLO, didn't really measure CLO. So we stick to the blue curve here. What you can see here at the left in the graph is even shown in the picture there. You have the ozone, a quite lack of ozone over a quite large part over the northern hemisphere, and that is due to the chlorine monoxide, which is at the same spot. at the same time. So that is the relationship between CLO and ozone. Now this is most of our instruments, which except from the LiDAR system, I have the possibility to run these instruments, and I have the responsibility to see to that there is liquid nitrogen available and that the instruments don't stop, because these are all instruments which should run 24/7. And I will now show a little bit of the DOAS instrument. This is measurements from the DOAS instrument from, as I mentioned already, from the Max Planck Institute in Mainz. And the instrument, DOAS instrument, is an instrument which looks just up into the sky and collects all the scattered light from ozone molecules on top of it, above it. So what we can see here is the result from 2023, and it is compared with two satellite measurements and a model. And you can see it's quite a good agreement between the measurements and the models and the satellite measurements, of course. So this is ongoing, and I think it goes back to 1995. We have this kind of data, and it is also interesting to show this because there are people out there who want to see these kind of long time series, and that is why we do have this monitoring approach for these guest instruments even. Does it go backward now? Okay. I will move now from the DOAS instrument to the millimeter wave radiometer. And that is the instrument which comes from the Karlsruhe Institute of Technology, and looks like that. I don't want to go into the details, the technical details here, but it just looks out through the window. The left picture shows that, and the electronics is next to the instrument. It has a small periscope sticking out through the window to the right, the upper plane, and the lower picture shows the inside of the vacuum dewar, which is cooled down to like 25 Kelvin or so. And the millimeter wave radiometer measures in the millimeter wave range. Of course, you are familiar with this kind of picture and the region. It comes up. I'm used to the frequencies, so I always put the frequencies on top of this picture. And the red rectangular shows the region where we can do microwave measurements, millimeter wave measurements. And they look like that. So you have spikes of ozone, and the blue stuff is water vapor, and it also shows that to higher frequencies to the left, the water vapor will be like a wet blanket. We cannot look through anymore. So we stay to the right at around 200 to 300 gigahertz and do our measurements there, just looking into the sky and looking for the radiation coming from the sky, from the ozone or from other molecules over there. And we call them the millimeter wave windows. This is Swedish. If you fly on an aircraft, then of course the situation looks a bit different. Not for the German aircraft at 3,000 meters, but for your aircraft at 10 kilometers where you fly, then you have most of the water vapor, 99% or so, below you, and all the signatures are showing up very nicely in the measurements, so you can go to higher frequencies. But if you sit on the ground, then you have to pick those lines which are visible and not too close to any water vapor line. But as you can see there's a lot of ozone lines that you can measure. It is emission lines which occur from rotational transitions of molecules, of ozone molecules, and there are quite a lot of these lines that you can choose. This is a typical measurement of my instrument. You see the ozone peak, the strong one, to the right, and there is a small CO peak, carbon monoxide peak, that I also measure since 10 years back or so. And these are time series that I have produced, well, quite some time ago. And we have, of course, newer ones, which I will show in a second. This is how our retrieval process works. For those of you who are not familiar with remote sensing, it's quite common to use this retrieval technique, which is called optimal estimation, and that means you put in a a priori profile. It is shown to the left, a profile of ozone that is a normal profile, and then you start you put in temperature and pressure as well, and then you start a model which gives you the spectrum as it should look like, that you can see on the top left of the right 6 panels there. And there is 2 lines actually. There is the measurement and the fit. So they agree quite a lot, quite well in the end. And then you just look into the model, how much ozone did I put in at different altitudes, and you get your profile out, and the profiles are now shown in the plot to the left. That's how the ozone layer looks like. And on this day, it was November 20 or something like that. The averaging kernels over at the right top, they show the sensitivity of the instrument. So I cannot really say that the value that I have at 25 kilometers is only from 25 kilometers, but it consists of contributions from like 18 kilometer and probably 37 kilometer as well. And that is the width of the averaging kernels to the right, which gives you the information there. But well, it's probably too technical. In the end, you have the profile, and you can to the lower left, and you can see the error bars there as well, or the error region. Okay, and doing that, that is a bit strange. I have compared these kind of measurements from the MIRA instrument, from the millimeter wave instrument, with satellite instrument, with MLS, and also with ozone sondes. There's something wrong here. With ozone sonde launches from nearby Sodankylä in Finland, and our measurements show quite some agreement, but there are also differences which we still have to work out why they are there. It's a bit weird. Something happened with the presentation here. Okay, but these are the latest time series that I also showed at the ozone conference, which is going on in Boulder right now. This is only 6 years of ozone, the last 6 years, and well, that is the task of my instrument, to do ozone monitoring even in the future. And to the right, you even have the Dobson units. Problem with that is, Dobson unit is probably familiar for you. It tells you how much ozone there is in a column on top of, in the atmosphere. The problem is that our measurements don't reach down to the ground. So there is some part missing. Between 15 kilometers and the ground, we don't see any ozone. So that is missing in the column, unfortunately. And that makes it a little bit difficult to to get some information out of these pictures to the right, the lines. But we hope that we will can compare with satellite measurements, and then we probably see how much is missing, whether there is a kind of a constant offset which we could add to our measurements, and then we would get it right. Okay. And this is what the DOAS instrument measures. The DOAS instrument measures the Dobson units from the ground up to the atmosphere, through the entire atmosphere. And we do the measurements from 15 kilometers upward. And that is what is missing at this particular graph, this particular year. I haven't done any more calculations there, but there is some hope that we can add a constant offset in some way, and then we get a consistent build of the Dobson unit, and probably can give this as information to the general public as well. Outlook, coming to the last slide here. This is again a little bit back to geophysical parameters, and probably coming back to other measurements which have been done at IRF for 50, 60, 70 years. This is an ozone measurement, and an ordinary ozone measurement at 235 gigahertz. This is oxygen at 234 gigahertz. And you can see two peaks there. And these two peaks, they appear when oxygen as a dipole molecule experiences the magnetic field lines of the Earth. And when the magnetic field lines are disturbed, when the solar wind comes and presses the magnetosphere from one end, then these lines, they can increase the distance, but they can also disappear a little bit. And that is the latest research that we started this year. And there's a PhD student working on this project. We'll see what comes out of that. Okay. With that, I thank you for your attention and wait for your questions.
Hey, thanks, Viva. That was a really great talk. Particularly some of the solar activity projects that you have going on. I think that our high altitude observatory lab would be quite interested in the work that you're doing if they're not aware of it already.
They should.
Yeah, they should. Are these data publicly accessible or through partnerships?
Oh, when it comes to my data, they are publicly available, not accessible, but available. If anybody asks for data, then I can give it. But we are planning to put the data, our data, the ozone data, on the NDAC network for the detection of atmospheric and NDAC climate change. Yeah, we put them on that database, and then they are available. I don't know about the community which works with the solar, wind, and the space research. But they are certainly available if you ask.
We have time for questions online and in person. Do we have any questions? I have a question. I kind of wrote it down. So your MIPAS instrument that you compared with MLS?
MIRA.
MIRA. What's your vertical resolution?
It varies a little bit because the resolution depends on the pressure broadening of the lines. At around 25 kilometers, I have a resolution of 6 kilometers at best. It's not better than that. That's
actually pretty good, because because MLS, the resolution of MLS is pretty coarse.
Oh, it's much higher than 6 kilometers. Yeah, it is. It is, unfortunately. But that is because MLS looks from the top to the atmosphere, and we look through the entire atmosphere. So we always have the broad contributions to the line in our measurements, while MLS can scan through and only picks the certain altitudes. And that is a big advantage if you have a satellite.
So are you validating your instrument to MLS, or is it the other way around?
No, we don't validate MLS. We do it the other way around.
The other way around?
Yeah,
Okay.
for now, the MLS is still the standard where we can check whether we do good with our measurements.
Okay. In like the lower stratosphere part.
Yeah.
Yeah. Hey, Karen.
Hey, Vy, good to see you again. So I would imagine there's a lot of manufacturers and researchers that want to give guest instruments to make observations at IRF. How do you all decide on which instruments can come to your institute?
We don't have a real policy there. It is more like the contact between researchers. So, for instance, the FTIR was installed at S-range first. The Fourier transform infrared spectrometer was installed there. And then they realized they don't have the support there. They don't have the scientific support. So they moved the instrument to our institute because there was some research going on for atmospheric research. And that was more like a personal thing between the researcher at IRF and the researcher for the FTIR instrument. So I guess if anybody wants to put up an instrument at IRF, then just ask, and we will find a way to accommodate that.
Okay, sounds like the Swedish way. Just help everyone.
Yeah, that's true.
That sounds pretty, you make it sound so easy.
It is.
Do we have any other questions?
That was a great talk. There's been some discussion lately about satellites and space debris, like satellites coming down and leaving pollutants in their upper atmosphere. Do these kind of instruments offer any hope for measuring what the contamination from these activities are?
I left the conference this morning when they were talking about this, the space debris and all the rockets that launch and all the satellites that are launched, and there will be 58,000 until 2030, and they all fall down, and they will bring a lot of chemistry into the stratosphere which hasn't been there. We don't do measurements of this chemistry, but we have recently put up some cameras which monitor meteoroids. And if you monitor meteoroids of the size of 2 centimeters or so, you can even monitor all the debris which is falling down or passing over you. And so we do that, and we contribute to the catalog of space debris in such a way. And IRF will also take on the role for the space safety awareness for Sweden as a authority, and do this kind of give information to everybody who wants to know about this. Yep.
So you showed one picture of your calibration lab or a calibration chamber. So some of the pictures that you've shown of the instruments, that looked like there were lots and lots of parts that go into comprising a single instrument. So my question is, how do you maintain calibration, the calibration of these instruments?
Oh, okay, the calibration of the satellite instruments, you mean?
Yeah, the calibration of your research instruments.
Oh, these are easy to calibrate.
Okay.
But for instance, the FTIR in the middle picture has a liquid nitrogen dewar, and for every measurement you do the calibration with or you cool down the Oh, no, that was wrong. You cool down the instrument, the detector, and once in a while we have you can see it here at the very right side, there is a black body. And the black body is that you can switch on, and then it goes up to 1000 Kelvin, and you do your measurements against 1000 Kelvin, and then this is your calibration. For the millimeter wave instrument, we actually, to the left here, we have a liquid nitrogen can hanging there. It says even liquid nitrogen mirror. And that is one way we calibrate our instrument. But so these kind of calibrations are quite easy because we always have some kind of calibration target that we measure against. And it is either room temperature or it is liquid nitrogen or something like, or 1000 Kelvin at the black body. It's much harder with the satellite experiments, of course. And there we do very thorough calibrations in our lab, also in these big vacuum chambers. But still, once they fly, it looks different. And then you have to react to that. If a spacecraft is out in space and you realize that certain particles which you should expect don't come in, then you might ask yourself what is going on. And then they realize that the spacecraft itself had a charging like 30 volts or something like that, and pushes away all the electrons which don't have enough energy to come into our detectors. So we are missing things in our measurements which we would have on Earth. And then you have to deal with that, and you have to adjust your measurements accordingly.
Well, if we have no further questions online and in person, it looks like we're close to the seminar hour. So let's please thank our speaker.
Thank you. You're welcome.